right, derivatives of exponents and logarithms. Let's start with the derivative of e to the x. Remember, e to the x is the natural exponential function. E is non-repeating, non-terminating. It comes from the definition of a limit. The unique thing about e to the x is that its derivative is the same, e to the x. Now, if you had e raised to a quantity, then we would need to use chain rule. So the derivative of e to the u would be e to the u times the derivative of u. So for instance, if we have e to the tangent x, then tangent is going to be our u. And so if tangent is u, then the derivative of tangent is what? Well, the derivative of tangent is secant squared. So if we follow that formula, e to the u times the derivative of u, then we're just going to have e to the tangent times the derivative of tangent, or secant squared. So e to the tangent times secant squared. All right, look at the next one. For the next one, we have two things that are being multiplied. So we have a product. So we're going to need to do first times derivative of second plus second times derivative of first. So first times derivative of second. So remember, the derivative of sine of a quantity is going to be cosine of that quantity, and then times the derivative of that quantity. So derivative of sine 5x is cosine 5x times the derivative of 5x. All right, so again, first times derivative of second plus second times derivative of first. So here's second. And so let's look at the derivative of the first. So the derivative of e to a quantity is going to be e to that quantity times the derivative of that quantity. So it's going to be e to the negative 4x times the derivative of negative 4x, which would be negative 4. So we could clean that up just a little bit. If you wanted to, you could move this 5 out in front. You could move this negative 4 out in front if I wanted to leave it in this distributed form. We also have a common factor of e to the negative 4x here and here. So you could factor that out. If you do, just put your finger over e to the negative 4x in each case, and what you have left will be your other factor. Now, which way should you write your answer? Well, it's really just a matter of, do you want it factored out where you can see the greatest common factor, or do you want it distributed through? Really, either one of those is perfectly fine. All right, derivatives of logarithms. Let's start with the natural log, since we were just working with the natural exponential. Remember that the natural log is log base e. So the derivative of ln x, or the log base e of x, is going to be 1 over x. So then the derivative of ln u, when this is a quantity, it's going to be 1 over u times the derivative of u. Now, if you think about that, 1 over u times the derivative of u would just put the derivative in the numerator and the original in the denominator. And so that's another way that you can think of this. If you're taking the derivative of the natural log of a function, it's going to end up being the original function in the denominator and its derivative in the numerator. So if you look at this first one, we could go through and we could use the chain rule and say, okay, this is our quantity, so we'll call that u. So that would be 1 over u times the derivative of u. So 1 over u, and now we need to multiply by the derivative of x cubed plus 1. So that would just be 3x squared. You'll notice, though, that for our final answer, when we multiply those two together, we end up with the original in the bottom and its derivative in the top. All right, look at the next one. Derivative of ln sine x. So again, we could put the original in the bottom and its derivative, cosine, in the top. And so what is cosine over sine? It's cotangent. All right, for the next one, we've got the square root of ln x. So first I'm going to rewrite that to get rid of that radical. I'm going to rewrite it with an exponent so I can use power rule. So if you have a quantity to the 1/2, the derivative of the outside function is going to be 1/2 that quantity to the negative 1/2. So it doesn't really matter what's inside here. Anything to the 1/2 is going to be 1/2 that thing to the negative 1/2. That would be the derivative of the outside function. Then we need to multiply by the derivative of the inside function. The derivative of ln x is 1 over x. And so our final answer then, we could move that ln x down to the denominator and put it underneath the square root to get rid of the negative exponent. You could rationalize that if you wanted to get the radical out of the denominator. Now, we don't spend a lot of time on proofs, but we do like to throw those in where we can. And so the proof that the derivative of ln x is equal to 1 over x is pretty straightforward. First off, remember that ln x just means the log base e of x. So if we switch that logarithm back to its x form, that would be e to the y equals x. E to the y equals x. So that's the same thing. That's the derivative of ln x, or that's ln x. So let's take the derivative of it, and to do that, I'm going to need to use implicit differentiation. So I'll take the derivative of both sides. The derivative of e to the y would be e to the y. And remember that anytime you're doing implicit differentiation in terms of x, when you take the derivative with a y in it, you have to leave a dy dx in there. So again, that's just our chain rule. The derivative of e to the y is e to the y. And since y wasn't in terms of x, then the derivative of the inside would be dy dx. All right, over here, derivative of x is just 1. So let's get dy dx by itself. To do that, I'll divide both sides by e to the y. And I have 1 over e to the y. And remember right here that e to the y was equal to x? So yeah, the derivative is equal to 1 over x. All right, so let's look at what if we have the derivative of a log that is not the natural log. It's not a log base e. It's a log with a different base. So for instance, we have a base of 10 here. That would be the common log. All right, so then here's the formula that we're going to utilize. And again, if as we have here, it's not just an x value, it's a quantity u, then we're going to use chain rule. So that would be 1 over u ln a times the derivative of u. All right, so we're going to do 1 over u. So again, u is 2 plus sine x, ln a, and notice that a is our base, so ln 10. That's the derivative of the outside. Now we need to multiply by the derivative of the inside. So we need to multiply by the derivative of du, the derivative of 2 plus sine x. So the derivative of 2 is 0, and the derivative of sine is cosine. So that would give us our final answer. All right, what if we wanted to take the derivative of an exponential that was not the natural exponential? So it wasn't e to the x, it was a to the x. All right, then that's going to be a to the x ln a. And again, if this is a quantity, I'm going to use chain rule. So if it was a to the u, that would be a to the u ln a times the derivative of u. So if you look at our problem, a is 10 and u is x squared. All right, so a is 10, u is x squared. So if we follow our formula, that's going to be a to the u ln a. So it's going to be 10 to the x squared ln 10. That's the derivative of the outside. Now we need the derivative of the inside. We need the derivative of u. So u was x squared. So the derivative of x squared would be 2x. And that would be our final answer. All right, the last thing we want to look at is something called logarithmic differentiation. And to do that, we need to remember our properties of logarithms. Remember that if you have the log of two things that are being multiplied, you can break that into two separate logs that are being added. If you have the log of two things that are being divided, you can break that into two separate logs that are being subtracted. And if you have an exponent on what you're taking the log of, you can move that out in front and multiply by it as a constant. All right, so let's take this natural log right here and let's expand it. Let's break it apart using those properties. So to begin with, in my numerator, I have two things that are being multiplied. So remember, when you have two things that are being multiplied, you can write that as two separate logs that are being added. All right, then it's being divided by this quantity. So remember that when you're dividing, you subtract. So I'm going to subtract that log. So now I have three separate pieces that are easier to work with. Also, we could rewrite the square root of x squared plus 1 as x squared plus 1 to the 1/2. So each of these exponents, 3/4, 1/2, and 5, each of those exponents now, we can use this property to pull the exponent out in front. And so that would give me 3/4 ln x. I'm just going to rewrite this guy for right now as x squared plus 1 to the 1/2, and then I'll pull the 1/2 out in front in our next step, just so we don't skip any steps and confuse anybody. And then we'll take this 5 and move it out in front as well. All right, so if we put our 1/2 out in front, that is our expanded form. Okay, why would I ever want to do that? Well, I'm going to use that in logarithmic differentiation. So they give me y is equal to this great big huge large equation or value, and they ask me to find the derivative. Okay, well, to find the derivative of that, I'm going to have to use product rule, first times derivative of second plus second times derivative first, and then I'm going to have to use quotient rule with that great big huge large thing I just got. The problem is we've got all of that multiplication and division making this so much harder. It'd be great if there was a way to get rid of the multiplication and division. Well, remember what we just did over here? If I insert an ln on both sides of this equation, as long as what I do to one side I do to the other side, that's a legal move. Remember, we have that property that if ln x is equal to ln y, then x has to equal y. So we haven't changed anything. But if I insert the ln on both sides, then I can replace this with what we just did over here with that expansion. So there's that same expansion. Now look how much easier it's going to be to take the derivative. Now I'm going to have to do it implicitly because I don't have y by itself over here. So let's take the derivative of y in terms of x. We have a separate video on implicit differentiation if you need to review that. So remember, the basic of implicit differentiation is when you're taking the derivative of y in terms of x, if you take the derivative of y, so like the derivative of ln y is going to be 1 over y, if you take the derivative of y, you have to leave a dy dx in there. So basically we're saying the derivative of ln y is 1 over y, and then we don't know what the derivative of y is because it's not in terms of x, so we just have to leave that in there for our chain rule. So derivative of outside times derivative of inside. All right, on this other side, bring our 3/4 down. Derivative of ln x, we learned earlier today, is 1 over x. Bring our 1/2 straight down. And the derivative of the natural log of a quantity, remember we have that shortcut that you put the original equation in the denominator and its derivative in the numerator. So the original equation is x squared plus 1 and its derivative is 2x. All right, bring that -5 down. And the same thing, we're going to put the original in the denominator and its derivative in the numerator. All right, so now I need to get dy dx by itself. So to do that, I'm going to multiply both sides by y. So on the left-hand side, I would just have dy dx. And on the right-hand side, I am multiplying by y. So if we clean this up just a little bit, you can see we could combine a few things here. I've got the derivative of y in terms of x is equal to this. But here's the problem. The derivative has to be in terms of x, and that is not an x. That's a y. Well, remember back in the very beginning, they told me what y was equal to? It was equal to this whole big quotient. So all I need to do is just replace y with what it's equal to. Replace y with what we started with up there. Now we have the derivative, and everything is in terms of x.